In the previous lecture, we have seen a very brief introduction to X-ray diffraction. You know, X-ray diffraction, as I have told you, is a powerful tool to study the structure of crystals. Now, today we are going to start the first concept of X-ray diffraction, which was actually provided by W.H. Bragg and W.L. Bragg in 1912. This is called Bragg's treatment. Actually, in this treatment, we will see Bragg's law or Bragg's equation, which is a very simple equation of physics, but its importance is very vast regarding the study of crystal structure. In fact, Bragg put forward a model which generates the conditions for diffraction in a very simple way. They pointed out that a crystal may be divided into various sets of parallel planes. The directions of diffraction lines can be accounted for if X-rays are considered to be reflected by such a set of parallel atomic planes, followed by the constructive interference of the resulting reflected rays. So you can say that the problem of diffraction of X-rays by the atoms was converted into the problem of reflection of X-rays by the parallel atomic planes. So whenever you deal the Bragg's treatment of X-ray diffraction and you use the term reflection, that means diffraction, and popularly it is called Bragg's reflection. So don't be confused that in this treatment the term reflection is used just instead of diffraction. Okay. So you can say the words diffraction and reflections are mutually interchangeable in Bragg's treatment. Okay. And based on these considerations, Bragg derived a very simple mathematical equation which is called Bragg's law. And we will see the deduction of this Bragg's law in this lecture, and we will also see what are the important characteristics of this Bragg's law. Actually, in a perfect crystal, X-ray scattering is elastic. When you say that X-ray scattering is elastic, what does it mean? It means there is no change of energy. Okay? Actually, Bragg considered the X-ray diffraction from a crystal to be reflections, as I have just told you, from the plane of atoms. And he argued that the incident X-ray beam is specularly reflected with the angle of incidence equal to angle of reflection from the parallel planes of atoms, and that diffracted beams are found to form maxima only when the reflections from the parallel planes of atoms interfere constructively. Okay? Actually, the inherent idea behind this is what? This is actually each plane reflects only a small fraction of radiation, like a partially silvered mirror, and these reflected waves then interfere in a constructive manner and produce maxima. Okay? So for your convenience, all these facts I have mentioned it here. I am just giving the reading for your convenience. You can see I have written, in a perfect crystal, X-ray scattering is elastic, there is no change of energy. Bragg considered the X-ray diffraction from a crystal to be reflections from planes of atoms. So I have told you that in this treatment, diffraction and reflection are mutually interchangeable. Okay? He argued that the incident X-ray beam is specularly reflected with I equal to R. It means angle of incidence equal to angle of reflection from the parallel planes of atoms, and that diffracted beams are found to maxima are formed only when the reflections from the parallel planes of atoms interfere in constructively. It means they interfere in constructive manner. And the inherent idea is that each plane reflects only a small fraction of the radiation, like a partially silvered mirror. These reflected waves then interfere constructively and produce maxima. Okay. Now, to derive the Bragg's law, let us see this figure. Actually, in this figure, I have shown that there is a set of parallel atomic planes uh, with interplanar separation equal to d. You can see all these lines are not actually lines, but they are planes, and these planes are parallel to one another. Actually, here in this figure I have shown three parallel planes, and these parallel planes are designated by the Miller indices HKL, and D you can see is the interplanar spacing. Okay. Now let us consider uh, that a parallel beams of X-ray, or you can say monochromatic X-ray, are incident on these planes, and I mark these. I have shown in this figure two beams only, which are marked by 1 and 2, and actually these X-ray beams whose wavelength we consider is equal to lambda are incident on the parallel planes at a glancing angle of theta. You can see here this angle theta, and this angle is also theta. These are the angles made by the incident beam with the planes, and the angle made by the incident ray with planes is called glancing angle. So actually Bragg's law is in terms of glancing angle, not in terms of angle of incidence. So I have shown here that these two parallel beams strike the plane at an angle theta, which is called glancing angle. And actually these beams lie in the plane of the paper. We consider it. Okay. Now after interaction with the atoms of the plane, the beams get reflected. Okay. So these are the reflected beams which I have marked 1 prime and 2 prime. Okay. These are the reflected beams you can see. And since the beams obey the laws of reflection, so again the reflected beams will also make angle theta with the planes. So you can see the figure I have shown that the reflected beams 1 prime and 2 prime are making angle theta with the parallel planes. Okay. Actually in this figure I have shown that these two beams have been reflected from the two successive crystal planes. And you can see the figure. Now, we have to think about the interference of these reflected beams which are parallel to one another. And you know, for knowing the nature of interference, that is either the intensity is maximum or it is minimum, definitely you have to know what is the path difference between the interfering beams before interference. Okay. Or phase difference. We deal with the problem of interference either in terms of path difference or phase difference between the interfering waves. And for getting the value of path difference between the two interfering reflected beams, let us do a construction. Let us draw a perpendicular AC. You can see the figure. This AC is a perpendicular which we have drawn from point A to the beam number 2, incident beam number 2. Okay. This perpendicular falls at point C, so the angle at C will be 90 degree. And similarly, we also draw another perpendicular from point A on the second reflected beam, and this perpendicular is AD, you can see. And so angle made by this perpendicular at point D will be also 90 degree. Now see the figure. Actually, the beam number 2 has covered a distance more than the distance covered by beam number 1 before interference. As you can see, before point A and C, the path length of beam number 1 and beam number 2 are equal. Okay? And similarly, after point A and D, the path length of two beams are equal. So it is obvious that beam number 2 has covered an extra distance equal to this CB plus BD with respect to the first beam. So what will be the path difference between these two interfering beams before interference? You can easily say, if we denote the path difference by the symbol delta, that delta will be simply equal to what? That will be CB plus BD. Okay? CB plus BD. And you can easily see from the geometry of figure what will be the values of this CB and BD. After knowing the value of CB and BD, when you will substitute those values in this expression, you will get the value of path difference between the interfering beams. Okay? And for this, now let us see the figure. As this angle at B made by the second incident beam with the plane is theta, so, and this AB, I have joined the two lattice points A and B. This AB is also the perpendicular distance between two planes. So angle made by AB with the second plane, this will be 90 degree. And since the angle made by second beam with the plane is theta, so this angle which I am showing in this figure, this will be 90 minus theta. And as angle at C is 90, so it is obvious from the properties of triangle that this angle BAC will be equal to theta. And similarly, you can see the angle BAD will be also equal to theta. So ABC and ABD both are right angle triangles. And the side length AB of these two triangles is equal to D. It is obvious. So from the geometry of figure, we can easily find what will be CB and BD. So let us see the calculation. You can see. Just I have drawn here the right angle triangle ABC here. As you know, this angle is 90 degree and angle at A, this angle is theta. And the length of the perpendicular AB is equal to D. So from this figure, if your aim is to find the value of this CB, we will use the expression for sine theta. From this triangle, you can easily see sine theta will be CB divided by AB, but AB is D. So sine theta is CB divided by D, and therefore CB is equal to D sine theta. Sorry. Again, you can see this right angle triangle ABD. Angle at D is 90 and angle at A is theta. You can see the original figure. And AB is of length D. So again, from this figure, when you will write the expression for sine theta, you will get BD is equal to D sine theta. So in this way, very easily we have calculated the value of this CB and BD. Okay, CB and BD from the geometry of figure. So let us substitute these values of CB and BD in equation 1 to get the value of path difference between the interfering beams of the X-rays. So what will be the path difference? Delta will be equal to d sine theta plus d sine theta. So that is, delta is simply 2d sine theta. So this is the path difference between the two X-ray beams before interference. Okay. Now, from the elementary theory of interference, you have definitely studied interference in your course on optics, that for constructive interference, that is when maxima is created, resulting intensity is maximum. For that, this path difference must be equal to an integral multiple of wavelength of the wave. That is, that must be equal to n lambda. So let us write the condition for the maxima, and that condition will be delta should be equal to n lambda, but delta is 2d sine theta. So 2d sine theta is equal to n lambda. And here n is an integer, as you know. And this n actually represents the order of diffraction or order of reflection, you can say, or order of maxima. Okay. This very simple equation, which we have obtained very easily in an elementary calculation. But this result is very important to study the structure of crystal, and this very equation is called Bragg's law or Bragg's equation. So Bragg's equation is very simple, you can easily remember it. Okay. Now, as I have told you that in this expression, which represents the Bragg's law, n represents the order of maxima or order of diffraction or order of reflection. Okay. So if we consider that n is equal to 0, then what will happen? Is n equal to 0 possible in Bragg's law or not? We can check. If you consider that n is equal to 0, then see this equation 3. Then 2d sine theta will be n times lambda, n is 0, so this will be 0. But as 2d is not 0, so sine theta will be 0 and theta will be equal to 0. When sine theta 0, theta will be 0, because you know theta is glancing angle, and this 0 will be less or equal to theta, and this will be less or equal to 90 degree, because glancing angle will be never greater than 90 degree. And between 0 and 90, when sine theta is 0, then theta will be certainly 0. But what physically this theta equal to 0 refers? Actually, this theta equal to 0 implies that reflection takes place in the direction of incident beam, which cannot be observed in the experiment. And that's why we simply say that 0th order maxima or 0th order diffraction or reflection cannot be observed in experiment. Okay. 0th order diffraction is not observed. Okay. So while using this Bragg's equation, we never take n equal to 0. So if n is not 0 but n is integer, then what will be the values of n? Apart from 0, you can write n will be maybe equal to 1, 2, 3, 4, and so on. When you say n equal to 1, it means you are talking about first order diffraction. N equal to 2 refers second order diffraction maxima, and n equal to 3 refers third order diffraction maxima, and so on. Okay. So 0th order maxima in accordance with Bragg's law cannot be observed in experiment, but the first order maxima, second order maxima, third order maxima, they can be observed. Okay. So this is Bragg's law. You can see the derivation of Bragg's law is very simple. It is very easy. But as I have told you, although law is very simple, but its application is very vast. When we will study the crystal structure on the basis of Bragg's treatment, you will see that we can analyze the structure of crystals using this very simple law. Okay. Now we will see something, some important characteristics of this Bragg's law. Okay. And all these characteristics are very important, and particularly for objective type of questions, all these facts will be very important. So see these facts very seriously. In first point, we say that Bragg's law is the consequence of the periodicity of a space lattice. If a space lattice has not the property of periodicity, Bragg's law will not occur. So you can say that Bragg's law is a consequence of the periodicity of a space lattice. Okay. But there is a simple drawback of this Bragg's law. Actually, Bragg's law does not refer to the arrangement or basis of atoms associated with the lattice point. If your aim is to know how many atoms are attached to the lattice point, how the lattice points are arranged, you cannot actually decide it by the use of Bragg's law. So this is just a very simple drawback of Bragg's law. And this is the second most important characteristic. We simply say that Bragg's law does not refer to the arrangement or basis of atoms associated with the lattice points. Okay. Now let us see the third important characteristic of Bragg's law. You know, according to Bragg's law, 2d sine theta equal to n lambda. You know it. And so you can write sine theta will be equal to n lambda divided by 2. Okay. Now, if you consider that we are given a particular value of n and d, it means you are considering a particular order of diffraction. Let us, for example, say first order diffraction. When you will consider first order diffraction, n will be simply equal to 1. If you are considering second order diffraction, this will be equal to 2. And for a given crystal, you know d is constant because it is interplanar spacing. So for a particular crystal, d will be also constant. But if you use the X-rays of different wavelengths, it means we will observe the maxima of a particular order from a particular crystal, but we will incident X-rays of different wavelengths on the same crystal. Then what will happen? Then lambda will be different, and in accordance with lambda, the sine theta will also vary. So from this result, it is obvious that in this condition, sine theta will be proportional to lambda. It means if you will use X-rays of longer wavelength, sine theta will be larger. And you know, when sine theta is larger and theta lies between 0 and 90, then theta will be also larger. So we can simply say that when lambda increases, theta will increase. And when lambda decreases, theta will decrease. So I have marked here, you can see theta decreases with decrease in lambda. For a smaller wavelength, this direction theta, which actually measures the direction of diffraction, that will be also smaller. Okay. So this is the third important characteristic of Bragg's law. Now, the fourth important characteristic of Bragg's law states that the intensity of reflected lines decreases with increase in value of n or theta. If n or theta will increase, the intensity of reflected lines decreases, not increases. So you can say the intensity of higher order maxima is smaller, and so therefore you can conclude that the first order maxima for which n is 1, which is the least value of n, the intensity of the first order maxima will be highest, and as the order of maxima increases, intensity becomes less and less. Okay. So this is the fourth important feature or characteristic of Bragg's law. Now let us see the fifth one. Again, you know from Bragg's law that sine theta is equal to n lambda divided by 2d. Now, if you consider in this case that lambda and d are constants, it means you are using a particular X-ray of a particular wavelength, you are using a particular crystal for diffraction grating, so that d will be also constant. In that condition, you can see that for a particular value of n, let us say for example n equal to 1, this sine theta will be equal to lambda divided by 2d if n is equal to 1. But as you know, sine theta has not unlimited values. If theta lies between 0 and 90, then sine theta lies between 0 and 1. You know, 0 is less or equal to sine theta and this is less or equal to 1. Okay. So you can say that sine theta cannot exceed 1. Its highest value, its maximum value is 1. And as sine theta is equal to lambda by 2d, so we can say that lambda by 2d is less or equal to 1. And therefore, we can say that lambda is less or equal to 2d. This is actually the condition for occurrence of Bragg's reflection. Bragg's reflection never takes, always does not take place. When this condition will get satisfied, that is, if the wavelength of the incident radiation will be less or equal to 2d, only then Bragg's reflection will take place. If there is a situation that lambda is greater than 2d, can Bragg's reflection will take place? Answer is no. For occurrence of Bragg's reflection, this condition must be satisfied. This is necessary and sufficient condition for Bragg's reflection, that lambda should be less or equal to 2d. In fact, we simply say that for Bragg's reflection, it is necessary that lambda should be of the order of d. Lambda should be of the order of d. Only then Bragg's reflection will take place. And this is just the general condition for diffraction, because here the crystal planes act as the diffraction aperture. So the crystal plane spacing must be of the order of wavelength of the X-ray. Okay. And you know that in general, the crystal plane spacing d is of the order of 10 to the power minus 10 meter or 1 angstrom. So you can say that for Bragg's reflection, wavelength should be less or equal to 2 angstrom. Actually, this implies that the Bragg's reflection will be most effective, or most effectively Bragg's reflection will take place when you say that lambda is of the order of 1 angstrom. Then Bragg's reflection takes place most effectively. Okay. And this is the reason that X-rays of this wavelength range, that is X-rays of wavelength of almost 1 angstrom, is always preferred in analysis of crystal structure, because when you will take in experiment X-rays of wavelength of the order of 1 angstrom, they will suffer Bragg's reflection, and then Bragg's law or Bragg's equation will be a strong tool to study the crystal structure. And that's why if a question is asked to you, why we use X-rays of wavelength of order 1 angstrom in experiment to study the crystal structure, what you will say? You should say that when lambda is of the order of 1 angstrom, then Bragg's reflection takes place most effectively, and so the Bragg's law then can be used for the study of crystal structure. Okay. Now, let us see. In the introductory lecture, I have told you that for the diffraction of visible light, we use different diffraction gratings available in your laboratory. But that diffraction grating is not suitable for the diffraction of X-rays. Now let us think. As you have learned that X-rays can be diffracted by crystals, or in other words, you can say that crystals act like a three-dimensional diffraction grating for X-rays. But is the converse true? Can you say that crystals can be used to diffract visible light? Answer is no. Crystals cannot be used as a diffraction grating for visible light because in case of visible light, Bragg's reflection will not take place because you know the wavelength of visible light is of the order of 1000 angstrom. When you talk about visible light, its wavelength range is 4000 angstrom to 7800 angstrom. Okay, and you can see this wavelength is much greater than 1 angstrom. It is 1000 times greater. 1000 times greater. And this is the reason that we simply say that Bragg's condition is not valid for visible light, and this is the reason that visible light cannot be diffracted by crystal because in this case lambda is much greater than 2t. Okay, so you have you can see how easily we can develop the Bragg's treatment of X-ray diffraction. What is Bragg's law? What are its important characteristics? So this was a very simple lecture, very simple concept, very simple for understanding this concept. But as I have told you repeatedly that this concept is much useful in discussing the crystal structure. Okay. So this was all about the Bragg's treatment of X-ray diffraction, and I hope you have definitely enjoyed this lecture. Thank you very much.